Okay, we are on part 3 of the chapter 19, and we're going to be discussing transverse and longitudinal waves. And there's two common types of waves that differ because of the direction in which the medium vibrates compared with the direction of travel. A longitudinal wave and a transverse wave. If I were to set up a sort of a long slinky. In fact, I have a video of this, and I'll post it uh, in on Canva. If I were to like squeeze parts of it, suspend it, squeeze parts of it, and release it, it would produce a longitudinal wave that would travel down the length of the slinky, bounce off the anchor point, and come back, and it would come back and forth. Now, the longitudinal wave is the movement is going along the path of the medium, so it's parallel to the medium. Whereas if I were to take that same slinky and vibrate it, move it up and down, I would cause these transverse waves to travel down the slinky, and so in the longitudinal wave, the wave is going along the medium, and a transverse wave, they're going 90 degrees to the medium. They're going up and down 90 degrees. So those are the difference between the longitudinal wave and the transverse wave. In something like an earthquake, they're called P waves, which are the longitudinal, and S waves. That stands for the primary wave and the secondary wave. The primary wave is the first one that is usually felt in an earthquake, and then the secondary waves, which actually do much more damage, are the ones that follow. So there's two types of waves that take place in an earthquake. I've never experienced an earthquake. My son has. He was at UCLA. He was an instructor at UCLA. That's where he did his graduate work, and he went through a few earthquakes. Thank God, none of them major. But so the transverse wave, the medium vibrates perpendicularly to the direction of energy transfer. It's side to side. So examples are vibrations in stretched strings of musical instruments, such as a guitar string, a piano string, a harp. Radio waves are transverse waves. The electrons move up and down the antenna, produce transverse waves. Light waves are transverse waves, and S waves, the secondary waves that travel in the ground, providing geologic information. They can tell from the propagation of the S waves, the secondary waves. The distance between adjacent peaks in the direction of travel for a transverse wave is its frequency, period, wavelength, or amplitude. Now look at the question. The distance equals length. So it's the wavelength, C. The wavelength of a transverse wave is also the distance between adjacent troughs or between any adjacent identical parts of the waveform. So the distance between adjacent peaks is the wavelength. The vibrations along a transverse wave move in a direction along the wave, perpendicular to the wave, both A and B, or neither A nor B. Now, transverse, they're going up and down, so they're actually perpendicular to the wave. The vibrations in the longitudinal wave, in contrast, are long or parallel to the direction of the wave travel. Okay, a longitudinal wave, the medium vibrates parallel to the direction of energy transfer. Backward and forward movement consists of compressions. The wave is compressed, and rarefactions, the stretched region between the compressions. Examples are sound waves in solid, liquid, and gas. Sound waves are longitudinal waves. Again, examples: sound waves in solids, liquids and gas, P waves that travel in the ground, providing geologic information. What they're showing you here is they're showing you a tuning fork, and these red dots are just the air molecules. So you can see how there's a when the tuning fork moves forward, it compresses these molecules. When it moves away, they're spaced a little more, so you have this compression, rarefaction, compression, rarefaction, compression, rarefaction, and it just continues down the tube. This is like a resonance tube. You can think of like a flute or a pipe organ, those types of things we used to do when I taught the 24, 25. We would set up these resonance tubes in the lab, and you would get these kind of groupings. Okay, the wavelength of a longitudinal wave is the distance between successive compression, successive rarefactions, both A and B, or none of the above. Let's just take a look at this little example here. You can see that the distance from here to here is about the same from here to here. So the compressions and the rarefactions, it's the same. Both A and B. So it's both successive compressions and successive rarefactions. Okay, and that's the end of part 3. So we'll end it right here.